Engineering statistics. This will be our second video on continuous probability distributions. We'll be doing lots of calculus today. So I wore my calculus Just Do It Nike shirt. Actually, it's not a Nike shirt, and we did take the Nike emblems and invert them, but Nike didn't know about it, so don't tell. All right, I'll give you some slides to look at. I don't want that here, that's in my way. All right, here we go. So we were talking in the last video about continuous probability distributions, and I'm just going to give you a whole bunch of different ones that have different applications today. When we want to calculate a probability, because a continuous probability distribution is actually a function, remember this, a discrete probability distribution is a setting whereby there's this random variable x, and x will take on whole number values starting at x equals 0, and then x equals 1, and x equals 2, and we just wonder how likely each scenario is, but it happens at the whole numbers. Whereas with a continuous random variable, x is some sort of measurement that the answer is like a time, the time to failure, or a length of something. And so we've got all these different possible measures for x, and it's on a continuum. And the way that we calculate probabilities with these continuous probability distributions is we find the shape of our data. You can see this data is shaped skewed to the right. And we find some function that will take on that shape. And then we rescale that over either -infinity to infinity, or 0 to infinity, or some other domain, so that the area under that particular domain is 1. And subsequent areas on intervals between the beginning and the ends of that domain are then parts of 1, or percentages, or probabilities. So basically, the nice thing about this is you don't have to worry about lots of different formulas for calculating probabilities. There's one formula for calculating probabilities, and that's just the integral, the area under the curve from something to something else. However, the different curves that model the different sets of data are varied and very complicated sometimes. So our integrals get really nasty, but you won't have to do ones that are too tricky other than reversing the power rule, use substitution, and a little bit of integration by parts. We don't do some of the more complex techniques of integration like trig substitution or partial fraction decomposition, fun things like that. So there will be a point where, although you can do the integral by hand with those techniques or some of the simpler techniques, I'll let you use your fnint command on your calculator. So know both, know how to do integration by parts and use substitution, but also know how to use your calculator to find an area. So last time we just talked about generic probability distributions that are continuous. We also looked at the uniform or flat horizontal one. It's real easy to find the area there because they're just rectangles. We will be looking at the normal distribution, but today we're going to look at the gamma distribution, and a specific instance of the gamma distribution is the exponential. So this is a subset of gamma. Chi-squared will come later. Today we'll look at log normal. We'll look at Weibull today, and we'll also look at a beta distribution. They're all similar. Actually, they're all kind of related to each other, but they have pretty complex functions. And then to calculate our probabilities, we will have to, again, integrate those functions, which isn't too bad. It's kind of fun. This is just a slide from last time whereby you see that if you want probabilities, you just take the area from A to B, and that's the probability that X, the measurement, will be between A and B. Also remember from the last video, if we want the mean or expected value of our continuous probability distributions, we just take the integral on whatever the domain for the probability density function is, and it doesn't always go from -infinity to infinity. It can be defined as something else, but on the whole domain, we take the integral of x times f of x dx. So essentially, it's kind of like we're doing this summing up of a weighted average, which is kind of an interesting thing. So just remember that this is the way to calculate an average on a generic probability distribution. However, when we get specific ones, we'll have shortcut formulas where we don't have to do this every time. All right, we're going to look at now the gamma function. It's not the gamma distribution, but it's a particular function that we're calling the gamma function. So gamma of alpha actually is an integral. This integral is the integral from 0 to infinity of x to the alpha minus 1 e to the minus x dx. And this is going to kind of command some of our different distributions today, but it's just a function that's going to be referred to. And one of the really nice properties, probably the nicest property of this gamma function, is that gamma of a constant, like gamma of 10, is actually 10 minus 1, which is 9 factorial. So if I wanted to do gamma of 10, I could either do the integral from 0 to infinity of x to the 10 minus 1 e to the minus x dx, or I could just do 9 factorial, which is way easier. So just remember that gamma of a constant is that constant minus 1 factorial. It's also nice to note that gamma of 1 is 1. And this is really interesting. Gamma of 1/2 is the square root of pi. I may or may not have you prove that in the homework, but kind of interesting and sometimes useful. And it's sort of strange to think that you could do like gamma of 1/2 kind of seems like it would be 1/2 minus 1 factorial, which doesn't really make any sense because factorial is a function of integers. And yet we can kind of bridge this gap between functions of integers like factorials and then this gamma function. But that's for math majors. And you probably just want to know, how do I use this? So let's take a look. This is actually the gamma distribution. This is a density function that you can see has the gamma function within it, but the gamma distribution is structured such that the area under this for positive x's is 1 based on these different parameters or constants alpha and beta. And the nice thing about the problems that we'll be doing is typically they just tell you this is a gamma distribution, here's alpha and here's beta, and they'll ask for a probability and you just find an area. So kind of commit yourself to looking at this structure, and you're going to see most of our structures today have like x to a power times e to some power with a constant out front. But again, if we're trying to find a probability and the gamma distribution is the model of interest for the particular application, then we'll just be integrating this. And look, beta to the alpha, beta and alpha are constants, so that's a constant. Gamma of alpha is really alpha minus 1 factorial. So all of this is just a constant that can get pulled in front of an integral. And then we have x to a power e to the minus x over beta. So when you integrate something like this, you start thinking about integration by parts because it kind of fits that structure of the integral of something times something else. And integration by parts reverses the product rule. But of course, you know and remember and love that because Calculus 2 is such a fantastic class. If alpha is 1 on the gamma distribution, then we have an exponential distribution. It's actually kind of nice. If alpha is 1, then we get x to the 1 minus 1. So this x to something really just disappears and we get an oversimplified version of the gamma distribution. So if alpha is 1, it's called an exponential distribution. Makes sense because then this goes away and we get e to the minus x over beta with a constant out front. That's just an exponential function like one that you've seen in pre-calculus probably years ago. And you can see, so here is an exponential function like this, and we can take that exponential function, and that actually is a model that's useful to us in probability theory and applications. But alpha is 1 and beta is 1. But if we go to that gamma distribution, we make alpha 2 and beta 1, suddenly we've got this skewed distribution. If we make alpha 4 and beta 1, you can see it starts to flatten and it starts to kind of normalize. We start getting some symmetry as alpha increases. The exponential distribution, which again is the gamma distribution with alpha equal to 1, is used in several applications. Here are some. The time between trucks arriving at an unloading dock, the time between transactions at an ATM machine, the time between phone calls to the main operator. What you're seeing is it's actually the measurement, the random variable would be time. And this actually has applications that tie in with the Poisson distribution. Because remember, Poisson was like how many things happen in a certain amount of time. which is discrete because you're counting the number of things that happen in a certain amount of time, assuming some sort of average rate. But now we're changing the question so that the answer is a measurement, an amount of time from one truck arriving to another truck arriving, or from one phone call to another phone call. So that's kind of interesting. And in fact, our next application, oh, here's the exponential distribution. I just talked through that. That's exactly the gamma distribution with alpha equal to 1, and it's way simplified, so that's good news. But let's look at an application here. Oh yeah, well, I guess we're not yet. These are the shortcut formulas for the mean and variance of the gamma distribution, so that you don't have to do that big, long expected value integral if you want the mean and variance. And then, of course, if you plug in 1 for alpha, you can see that you actually get something really simple, and those are the mean and variance formulas for the exponential distribution. Again, it's just exactly what is above, but with alpha equal to 1. Can we get to a problem yet? You'd hope so. Here it is. Okay, so this one we're going to use an exponential distribution, and an exponential distribution is useful in a Poisson situation where we change the question, and no longer is it a question of how many things happen in this given time interval, but rather the question will be, how long will it be until the next whatever, until the next failure, until the next car in the drive-through, until the next phone call. So time to failure is typically what they call this. And if you're in a Poisson situation, you have some sort of assumed constant rate, and beta in a Poisson distribution, I'm sorry, beta in a gamma function is 1 divided by the Poisson rate. So we've got beta in our formula. And remember, an exponential distribution by default means that alpha from the formula is 1. So if you can pull back that formula, maybe you want to grab this formula and pause the video. Where is our formula? There's our gamma. And here's our exponential distribution. If you want to write down, you can pause the video, you can write this down. This is what we're going to use and integrate to try to answer this question. But this is actually a pretty complex question. So remember, beta is 1 over the Poisson rate. And the Poisson rate in this particular problem, here it is, oh, they just give us beta equals 5. So the Poisson rate, I guess, would be 1/5. But beta is 5. So we can plug 5 in for beta into the gamma distribution. And the interesting thing about this question, so we've got a system with components whose time in years to failure is capital T, that's our random variable. Our measurement is the time until failure. We're going to use an exponential distribution. Beta is 5. And then they actually give us a second part to this question. I often put a question like this on exams, so you might want to put a star on this. There's a second part that says, if 5 of these components are installed in different systems, what is the probability that at least 2 are still functioning at the end of 8 years? So that question is actually a binomial probability question with n equal to 5 and x equal to, well, it says at least 2, so that would be 2 or more. But we don't have p. We don't have the probability of still functioning, the probability, I guess, of not failing. So we have a question that's a binomial question, but we're without the probability of failure or success, and we're going to need to calculate that. What is the probability that a component is still functioning after 8 years? That would be, it's still functioning. The measurement to failure is 8 years or longer, I should say. So what we can do is we can first use the exponential distribution and find the probability that t is 8 or more, and then we can use that probability in the binomial calculation for at least 2 still functioning out of 5. It's a pretty complex problem. So let's give a look at this. I'll stop my share so you can see my whiteboard. So what I've done the probability that the time to failure is greater than 8 years would be the area under this exponential function from 8 to infinity of, and this is 1 over beta e to the minus x over beta, and beta was 5. Alpha is 1 because it's an exponential distribution. And you probably remember how to do this from Calc 2, or even at the end of Calc 1, you might have got to this. This is a u substitution integral. And so if u equals, here I'll even write that, if u equals minus t over 5, then the derivative of u is minus 1/5 dt. And so remember, this is reversing the chain rule. And if I have a minus 1/5 dt, which I can have if I want it, it's just going to cost me an extra negative out front. Minus 1/5 dt is that du. So this is really just e to the u du. I got a negative out front. And if I really want to, I can change the limits of integration. Remember, if this is a t value, and I'm going to change that to a u value, when t is 8, what is u? Well, u would be negative 8 over 5. So negative 8 over 5. And then when t is infinity, u would be negative infinity over 5, which is just negative infinity. And of course, we know the integral of e to the u is just e to the u. So we've got e to the u with a negative out front. We're evaluating from minus 8/5 up to negative infinity. And so that equals negative e to the minus infinity. So that's 1 over e to the infinity. That's going to go to 0. I put the negative out front, and then so minus e to the negative 8/5. So this is going to go to 0 right here. And then we've got a minus minus, which is a plus. So positive e to the minus 8/5. I think I did that out in my notes, and I got 0.2. So 0.2. What that means is the likelihood that the time to failure is 8 years or longer is 20%. And that becomes the p-value, the probability in a binomial experiment, because remember, the question was actually, if we have 5 components, and I guess this is the probability that they last longer than 8 years, what is the likelihood that at least 2 last longer than 8 years? So actually, if we did 1 minus binom CDF of n comma p comma, let's see, it says at least 2 would last longer than 8 years. So how about putting a 1 right there? Does that make sense? So 100% minus the binomial probabilities for x equals 0 and 1 would be the likelihood of x being 2 or 3 or 4 or 5. And it turns out that that ends up being 0.2627. So that, I think, is a pretty tricky question. You can go back if you want to, and you can look at the problem. You can pause the video. You can look through this again. But as I said before, I actually think this is a pretty important question because, well, it's interesting. It's a good application, and I might put it on a test. So be ready for that. Right. Let's see what else we got here. Oh yeah, there's a slide from the solutions manual so you can look at what we just did. And that can be helpful. You can always pause the video and take a picture of the slides if you want to. So essentially you've got all these slides. All right, so alpha was 1 in the exponential distribution. And for that particular application we just did, we used a gamma distribution with alpha equal to 1, which was the time until the next Poisson event. But if we want to extend that application, make it a little bit more complicated, then we can say, But what if alpha is 2? What if alpha is 3? What if alpha is 4? And so the similar application would be how long, so x would be our random variable, it's a measurement, how long until the next number of Poisson events, the next 2 calls or the next 3 calls or the next 4 calls. So the number of Poisson events is actually alpha, which is why in the last application alpha was 1, because it was until the next phone call or the next failure, something like that. So we will use a gamma distribution modeling the time until a specified number of Poisson events occur, where beta is 1 over the Poisson rate and alpha is the specified number of events. So let's see if we can do this one. We've got telephone calls arriving at a switchboard following a Poisson process with an average, here's the Poisson rate, of 5 calls coming in per minute. So you can see beta is 1 over 5. What is the probability that up to a minute will elapse by the time 2 calls have come into the switchboard? So up to 1 minute by the time, see, 2 calls would be alpha, right? So up to a minute would be, remember this gamma distribution starts at 0 and goes out to infinity. So up to a minute would be between 0 and 1 minutes. And let's look down here at the gamma distribution. So beta is 1 over 5 and alpha is 2. So we're going to have a 1/5 squared here. Gamma of alpha is really alpha minus 1 factorial, but alpha is 2. So gamma of 2 is actually 2 minus 1, which is 1 factorial, and that's just 1. So that's going to be nice. X to the alpha minus 1, that's just 2 minus 1, so that's x to the 1. E to the minus x over beta, but remember beta is 1/5. So minus x over 1/5 would be minus 5x. So I'm going to erase my board and I'll write down what I just said verbally, but you try to do it while I'm writing that down. All right. So, and notice the 1 over beta to the alpha times gamma of alpha is a constant. So I can throw that in front of the integral if I want to. So the probability that x is between 0 and 1 minutes equals 1 over beta to the alpha. So that would be 1 over 1/5 squared times gamma of alpha, so times gamma of 2, times the integral from 0 to 1 of x to the 2 minus 1, which is just x, times e to the minus x over 1/5, which is minus 5x dx. Okay, it's on my board now. I'll stop the share. And let's see if we can walk through this. So that's what I just said verbally. Hopefully you got that on your paper. And what you'll probably notice here is this is a product of functions. If I decided to try to make this u negative 5xu, then du would be negative 5 dx. And there's an extra x sitting here, which is not that great, unless you know integration by parts, and we do. So integration by parts, I'll just write this out real quick, says that if you have the integral of u dv, that's equal to u times v minus the integral of v du. So if you have the integral of a product, you actually can trade this problem right here for this problem right here. And our hope is that this problem right here would be easier to do. And actually what it ends up doing is typically, if we are in a situation where we can do this, is it ends up giving us an integral where it reduces the power on the algebraic expression by 1, and thus it would be an integral that we know how to do versus an integral that we can't do. But the trick in this is to pick u and dv, remember from Calc 2, pick u and dv in such a way that we can create v and du. So in this particular problem, u is going to be x and dv is the rest of it. dv is going to be e to the minus 5x dx. I know that's kind of small, sorry about that. So we pick u and we pick dv. Now, how do you pick it? There's an acronym called LIATE, L-I-A-T-E. It's an acronym for choosing u. You probably have heard this in Calc 2. It's the acronym for choosing u. And so if you have a log function in here, that's your u. If you have inverse trig, that's your u. It's a priority list. If you have an algebraic expression like x, that's your u. Trigonometric, and then exponential. E to the x, you never want to choose to be your u because you want u to be something you can easily differentiate. And the rest of it, whatever dv is, you want to create v, so you hope that you can take the antiderivative of dv, which is why you love e to a power, because you can easily take that antiderivative. So this, almost all the applications in the stats class, it seems like you're going to get x or x to a power, and that's going to be your u. So u is x, and that means du, which is really du over dx, equals the derivative of x, which is 1, but then I always multiply the dx to the right side. So instead of writing du over dx equals 1, I just write du equals dx. And then the antiderivative of dv, we sort of did a problem kind of like this. It's a u sub problem. I call it a baby u sub problem. So e to the minus 5x, the antiderivative of that is actually, v would be negative 1/5 e to the minus 5x. And if you take the derivative of this, you can see that that's what we have here. So the derivative of this would be e to the minus 5x times negative 5. And that negative 5 times negative 1/5 would be the positive that you need. So verify that if you need to. Come into office hours if you're not getting this. All right, so now we can make this problem turn into this problem. Let's clean up the constant out front. So 1/5 squared is 1/25, but it's on the bottom of a fraction. So the 25 can flip to the top of all of this. Gamma of 2 is actually 2 minus 1 factorial. So this is just 1 factorial, which is 1, which means this whole entire thing can turn into 25. So instead of writing 25 times udv, we can write 25 times uv. So that would be x times minus 1/5 e to the minus 5x. So I'll write that constant out front, 1/5 x e to the minus 5x. uv minus the integral of v du. So let's see, the integral of v du. So how about minus 1/5? I'll pull that out front of the integral. E to the minus 5x, and then du is dx. And we're evaluating this whole entire thing actually from 0 to 1. So I suppose we could put the 0 to 1 right here. But we need to remember that right here, we're still evaluating this part from 0 to 1 also. All right, well, what can we do with this? This actually right here, e to the minus 5x, I know how to integrate that. I just did. So this integral right here, do it in orange because orange is feeling left out. This integral right here turns into minus 1/5 e to the minus 5x. I just did that problem. So let's see if we can clean all of this up. We've got a 25 parentheses minus 1/5 x e to the minus 5x, and then negative, negative, that's a positive. So plus, we're going to have a 1/5 here times a minus 1/5. That's actually minus 1 over 25. And then we know we're going to have e to the minus 5x evaluated from 0 to 1. So this seems crazy. If you plug 1 in, that's actually 1 and 0 are about the two nicest numbers you could have in this problem. So you plug 1 in for x, and that makes some things kind of nice. You plug 0 in for x, that makes things really nice. And you do all of this with 1 in there, all of this with 0 in there, subtract them both, and let's see, what do you get? You get, I wrote it down, you get 0.96. So there's a 96% chance that there will be, what was it? 2 Poisson events within a minute, right? 2 Poisson events. It's been so long, I forgot the problem. But such is life, right? The other thing that I would say here too is that took a while. You do need to know how to do integration by parts. You need to know how to do U substitution integrals. However, you don't need to do them every single time. So once you've made sure that you can do them and you're working on the homework and you're like, geez, I keep doing integration by parts or whatever, you can use fnint, your numeric integration command on your calculator. And so some of those problems you can use that command for. Then when we get to the test, I'll probably have you integrate once or twice by hand. And then the other integrals that you need to take, you can just use the fnint command. All right, we're getting close. I wanted to go through a couple of other types of distributions. So we talked about the gamma distribution and the exponential distribution, which are related to each other. And they're both used in Poisson events or Poisson situations where you change the question. And the answer to the question is an amount of time until something happens or multiple things happen. There are other applications. By the way, there's the solutions manual for the problem we just did. You see they didn't actually write out all the integration by parts, but that's okay. So we've got a beta function. And notice this is a beta function, just like we have a gamma function, which gives birth to a beta distribution, just like the gamma function gave birth to a gamma distribution. The distribution is the probability distribution that we find the area under, and that distribution is related to, in this case, the beta function. And you can see the beta function is just a ratio of some gamma functions. So if we do something with gamma functions, we get this new function called a beta function. And the shortcut formulas for the mean and variance are here with a beta function. The beta distribution, so that's a different word, looks like this. So it's 1 over this beta function. But again, we see this x to the alpha minus 1. And then instead of getting e to the minus x over beta, it's a little different because it's a different function. And there are applications of beta functions and beta distributions that you'll see in the homework. The nice thing is they'll say, hey, this is a beta distribution. So you'll just grab this distribution and you'll integrate it to find your probabilities. Probably on this one, you'll be wanting to use fnint because that looks disastrous, depending on what alpha and beta are. There is also a log normal distribution. Look at that. That's a good time. So Carl Friedrich Gauss came up with the normal distribution and the associated function, which will come later, but the log normal, which is related, and there are actually tables in our book that we can use for finding areas, because this is just tedious, not only to integrate, but to actually, to integrate by hand is terrible. To integrate using your calculator is still kind of bad because you got to type all that stuff in. But log normal distribution has a mean and variance. It's got some shortcuts, and there they are. This is just like there's jillions of different distributions that fit particular sets of data. And so in real life, what you might end up doing is finding some other model with some other equation and scaling it so the area underneath the curve is 1, and then using intervals of interest and areas to calculate probabilities. So there's just countless different distributions. Our book runs out, I think, after, well, I guess there's some others later, but the Weibull distribution is another one you can see. Looks maybe a little bit more like the gamma distribution than the beta distribution because E comes back in. But look at how terrible these formulas are, the mean and variance. At some point, the math is pretty easy but tedious. So you can just plug stuff in and do your calculations. You get what you want. One of the nice things about the book and how it treats the Weibull distribution is it gives us a capital F function So in other words, the capital F function, remember, is a CDF. It's a cumulative function for area with continuous distributions. And that means it's doing the integral of this for us. And here is the capital F function for the Weibull distribution. So capital F means the area, these are for positive x's, so the area from x equals 0 up to whatever your input is can be found in this little short formula. 1 minus e to the negative alpha x to the beta. And again, alpha and beta are just constants. They're just numbers. They're positive numbers, you can see here, but they're going to give those to us. And they're going to tell us to use the Weibull distribution. So not that difficult. Let's do one application, and then we'll call it good for the day. The length of life in hours of a drill bit in a mechanical operation has a Weibull distribution with alpha equal to 2 and beta is 50. Find the probability that the bit will fail before 10 hours of usage. This is actually a personally interesting question because I just used a drill bit. I have a brand new guitar, and I installed a pickup in that brand new guitar, and I had to drill a 1/2-inch hole in that brand new guitar, a 1/2-inch hole and 2 1/8-inch holes. And it was a little bit scary, but it actually turned out pretty good. So pretty exciting. Let's talk about drill bits. All right, so this is a pretty straightforward question. They give us alpha, they give us beta. They tell us it's a Weibull distribution. We want a probability that the bit fails before 10 hours of usage. So that'd be from x equals 0 to x equals 10 hours. But look, we literally have this function right here. So it would be f of 10 equals 1 minus e to the negative alpha x to the beta. But look, we already know alpha is 2 x to the 50th. So all you have to do to answer that question is plug 10 in for x, 2 in for alpha, and 50 in for beta. And when you do that and type that into a calculator, you get essentially 1. Because essentially it's going to be 1 minus e to some negative power that's really big. 1 minus 1 over e to something big, that's going to go to 0. So you're essentially going to get 1 in that question. And what does that mean in context? That means it's pretty much 100% assured that you will get less than 10 hours of usage from the drill bit. The question then would be, is this like constant usage, or is this just, I was using this for a while in a procedure? But I'd say maybe it's constant usage. Maybe it's in a factory or something. Anyhow, some pretty good problems, a lot of fun calculus. I hope that made sense. Look over the homework, ask me some questions. We'll practice more later. Have a great day.